different aspect of information retrieval and how these different aspects are taken care by or taking addressed by different aspects of machine learning. So on the very first day, we have two sessions on basically highlighting the theoretical aspect of machine intelligence for IR or information search actually. So rightly on the fourth day, we have on the fourth day onwards actually, we have planned to highlight the different machine intelligence or different machine learning techniques which can be used for information search related issues or information retrieval related issues. So I think I mean Dr. Saroj is the I mean as per my understanding, as per my experience of previous experience of listening to him, he is the best person to offer a very fundamental way of explaining the different machine learning techniques. So we have privileged to have his expert in the previous one of the previous event, which happens in the month of July, and in that event also it was a encouraging experience that how you can model a particular machine learning technique uh, to solve some issue, to solve some application, right? So I formally welcome Dr. Saroj Kumar Biswas for our FDP, and let me share the citation of experts with our participants. So Dr. Saroj Kumar Biswas is currently working as an assistant professor in computer science and engineering department, NIT Silchar, uh, since the year of 2010. His current research interests includes machine learning, artificial intelligence, and its application for different scenario or different application domains. And basically, he published around total 36 international journal, including 20 SCI index journals papers, and in various reputed publication houses, including Elsevier, IET, Springer, World Scientific, etc. So his total publication around was to around 70 publications, and as far as PhD concerned, he is currently guiding 707 PhD scholars, out of which two has been already submitted PhD, two has completed and two has submitted it. And under this project umbrella, he has completed one of DIT sponsored R&D project, and currently supervising on one project sponsored by NPIU World Bank, which is again a R&D sponsored R&D project. So I formally welcome Dr. Saroj for this FDP, and from here I would like to hand over the session to Dr. Saroj. Yes, sir, please.
Thank you, Vikram sir, for this encouraging introductions about me. Thank you for that. So, looking for the session now. Here, am I audible, everybody?
Yes, sir. Yes, perfectly audible as well as visible. Perfectly.
Okay. Invisible password. So here, in this presentation, my endeavor is to model an evaluations of machine learning system. Whenever we devise or whenever we say make one machine learning system model, how we should model and how to evaluate that one, and different kind of issues are there to model and to evaluate one machine learning model. So we are going to talk about all these issues, and finally, we'll be talking about the decision tree. It's a mathematical part, how the decision tree is made, why decision tree, all those things we're going to talk about. So this is about the brief about my presentation here. So the name of the FDP program is Machine Intelligence for Information Retrieval. So machine intelligence is there for information retrieval. So any kind of information, it can be text, it can be image, it can be numeric, it can be anything. But whenever the term comes information retrieval, mostly it describes the text actual informations. But here, just I'm going to talk about in the first sessions the numeric data, but in the second sessions tomorrow I will have, then I'll talk about say textual data, how to handle using machine learning. So machine intelligence means in machine learning. So first PPT says here why machine learning, because nowadays everywhere whenever we talk about So research, the people say the machine learning. So everywhere we try to use machine learning. But now the questions, why machine learning? Where machine learning should be used? For some defined tasks, if the algorithms are available, for them machine learning is not required. For an example, if we're having sorting tasks, for sorting we have well-defined some kind of algorithms. In such a process, machine learning is not used. And for which process machine learning is used? Machine learning is used for the places where there is no defined algorithm for the task, but we're having huge amount of past historical information. But we know what we want to do. What we want to do, we know our target, but we don't have any algorithms. So in such process, actually, machine learning is used. For an example here, if we want to separate or categorize between the spam emails and the legitimate emails, actually we don't have any particular algorithm that this algorithm has to be used. So whenever we have a chunk of emails, some of them are say spam emails and some of them are say legitimate emails. From those emails, we can use some kind of machine learning tool there, machine learning programming paradigm, so that it can find certain kind of patterns from the emails which belong to spam, and certain kind of patterns from the emails which are legitimate emails. So whenever it finds, then for the spam emails, it can find the different categories, different kinds of patterns, and for the legitimate emails, it finds different kinds of patterns. From those patterns, whenever some new email comes, then this machine learning model can easily differentiate which one is the spam email and which one is the legitimate email. So in this case, actually, we don't have any particular algorithm. Trying to understand, we have huge amount of past historical information. From those informations, it tunes some parameters. Using those parameters, it can find whether the new email is a spam or it is a legitimate email. Now the question is how we can find those parameters. For different style, for different kind of algorithms, there are different kind of parameters. The objective of machine learning is to fine tune, to find the optimized value of those parameters. Now, why is machine learning? Already talked about why machine learning. What is that? Different researchers have defined it in different ways. Here we have the two definitions. One is the Tom Mitchell, and this is most popular. Most of the researchers, they define this one, but I would like to define this for this one. This is given by Tim Offering. Here it says, machine learning is programming computers to optimize a performance criteria using example data or the past data. It says that we need to have the past data. From the past data, the objective is to optimize the performance criteria. Now, those performance, it can be any kind of performance criteria, right? This performance criteria is totally dependent on model parameters. So if we can find or if we can optimize the model parameters, then we can optimize the performance criteria. Now for the different algorithms, the model parameters are different. For an example, if we talk about neural networks, in neural networks, the model parameters are the weights. So if we can find the weights properly, so that if the task is a classification task and we can find the decision boundary and we can classify the task properly with some weights, then we can say these weights are optimal weights. So whenever we get the optimal weights, then those weights can be used to find or to optimize the performance criteria. In that case, the performance criteria can be error rate or can be the accuracy. So the main thing, if we talk about the machine learning says that we need to have past statistical information, and from those past statistical information, our objective is to find or to optimize the model parameter values. And using those model parameter values, then we can optimize the performance criteria. And in the second definition, actually, one thing is added. It adds that the performance of the system is improved with experience. It is written here only. If we read the thing is same, but one thing we change here, it says that with time or with experience, the performance is improved. And this is true in most of the cases. You can see, say, in neural network, if you see 10 iterations, in 10 iterations, whatever it is you have achieved, if the number of iterations is increased, then we get it's a better accuracy. But again, we can say that if we increase the amount of past statistical information, then again we can get more better accuracy. For example, if the database size is say 5,000 samples are here, And now if we increase it to say 10,000, then get in on an average, then we can see that the accuracy of the model, accuracy of the algorithm can be improved. In that way also we can describe it. So after that, these are the basic things, because the basic things I have to discuss, then we talk about how to model machine learning model. These are the classifications of machine learning algorithms. Basically, most of the literatures and most of the books, the machine learning is classified into three categories, and these categories are supervised, unsupervised, and reinforced. In supervised, generally two popular tasks are there, and the classification and regression. They belong to supervised. In unsupervised, we have clustering and association rule mining. These are most popular tasks under unsupervised learning. And then the reinforced is called actually Q learning. There are different kinds of algorithms we're going to look all those things. The first one is the supervised. So if the data sample is like that, then we can say the learning is supervised. Actually, if you see this data sample, we are having here, these are the independent parameter, independent attribute, and we are having here one dependent. Means we're having one, if these are the values, then what should be the outcome? The outcome is given here. So that is a class here, the classification problem. So if you see all the vectors, all the patterns, you can see that the label is given here. Label is given here. It means these are the independent parameters, and this is the dependent. Means what should be the outcome? The outcome is given here. So one supervisor is given here, one master is given here. Whenever the model is trained, then it can check whether we are getting the exact output or not, because we are having here whether this is yes or no. So if the data is like that, and if the machine learning is trained in such a data, then we can say that is supervised learning. And nowadays we're having a number of popular supervised learning algorithms in machine learning, and these some of them are given here. So name-based algorithms, then we have a decision tree, and the decision tree is having different kind of versions of the versions, ID3, C4.5, C5.0, card, these are the versions. And then we have support vector machine here, artificial neural networks, k-nearest neighbor. Here we CNN means deep learning neural network is not covered. I didn't give here, but today especially people are working on the deep learning, because now using deep learning we can model the human intelligence in more better way. And then unsupervised, if the data sample is like that, you see here the data sample, we're having the patterns, there's the name of the patterns, x1, x2, x3, x2. These are the observations, and these observations are having some attribute values. These are the attribute values. So here data sample x1, it has a1, a2, a3, all values are given here. Similarly for x2, values are given here. You can see here no classification, no label is given here. Label is not given here. So if we have this kind of data, and if some kind of training is done there, so then we can say that is unsupervised learning. So what kind of training is done here? Because we don't have any class. So here actually it trains and it finds the interrelationship between all the attributes or the regularities. What kind of regularities are available within the patterns? This kind of regularities are estimated, and that is also called density estimation. It finds the relationship between different kind of attributes. And now to do those things, we're having a number of algorithms, and these are the algorithms. The clustering we have here, K-means algorithm, K-medoid, Cure, and Beat. K-means already we know. K-medoid, there is some problem in K-means, that's why K-medoid came in existence. But both algorithms finds a spherical shape. If the cluster is spherical, then we can use K-means and K-medoid. But keep in mind, in some of the cases, the cluster are not spherical, they're non-spherical. If it is non-spherical, then we have another algorithm that is called Cure. Using Cure algorithm, we can find cluster whose shape is non-spherical. And then we have a bit here. And this algorithm, this clustering algorithm, is very much useful in case of image processing because it can compress. And then unsupervised, we have an association, rule mining. So there are some popular algorithms. These are the popular algorithms. A priori algorithm, predictive a priori algorithm, the Tertius and the Leclerc. These are the algorithms. And now the reinforced learning, reinforcement learning. What is that actually? So we are having here the data pattern. See here, this vector, and here we are having vectors. We are having independent parameters, right? With independent parameters, we are having certain kind of penalty functions or a reward. Certain kind of values are given here. Certain kind of values are given here. Try to understand. So here we don't have any class 1, 2, 0 like that. Here we have the reward or penalty. What is that actually? So when the system takes one move or one directions, then it checks whether the direction is in the right direction or the wrong direction. If the direction is the right direction, then the system is given a reward, or the system is rewarded. Whenever the system is rewarded, it understands that we are in the right direction. If the system is not in the right direction, then some penalty function given here. So whenever some value is penalized, then you can understand that we are not in the right directions. In that way, generally, it searches the path. Actually, whenever we talk about any kind of machine learning algorithm, it finds a such as a path to solve a problem. So here, in case of reinforcement learning, we can say the movement of a robot. The movement of a robot can be, we can have a source here, we can have a destination here. So one by one, it can reach, one by one, it can go, so it can reach to the destination. So in that case, if the robot is in the right direction, some reward can be given. Or if it is not in the right direction, some penalty functions can be given here. Now the question, how we can give the reward and penalty there? So reward and penalty, we need to devise one algorithm of equations. From these equations, the reward and the penalty functions can be given here. So whenever you have a system, so you can devise the penalty functions or the reward if you use a reinforcement learning. So now some of the popular techniques which belong to reinforcement learning, these are RBM, random Boltzmann machine, deep belief neural network. This it belongs to reinforcement learning. And one of the most prominent algorithms is a deep Q network. This is reinforcement learning. Keep in mind here, the concept of CNN neural network is used here. So if somebody is interested in working with say reinforcement learning, they can work here. So if we talk about any adaptive kind of learning, adaptive kind of system, the adaptive kind of system is made based on reinforcement learning. So if somebody is new, a newcomer in machine learning, they can use the reinforcement learning to devise new algorithms so that you can solve adaptive kind of problems. So these are the categories now. Now coming here. So now the question is, if we want to make one model using machine learning, and what should be the pipeline or what should be the flow? Now keep in mind just here, I'm going to talk about for the numerical data. I mean, you can say it's a model of for the data science. If the data is numerical data, and if the data is textual data, then the flow is a bit different. The next step we will see on that. And again, keep in mind, if it is an image processing, image kind of say tasks, or if we want to do some image processing tasks using some machine learning, then this flow will change. The flow is same, but the nomenclature can be different. For an example, in pre-processing, in image processing generally, we do noise removal, we use image enhancement, those kind of things we do. But here, we just while you're looking here, this model is totally dependent on the numerical data. So in the numerical data, if the model is like that, and how we can model, how we can do. So initially we have a data set here, right? So data set, you have to make the data set. If it is say some kind of textual or the image processing image data, if it is textual, then you can construct the data set, or you can refine the data set, because we can in the textual data we can have number of features, we can construct the features that we can make the data set here. So in some problems, in machine learning problems and data mining problems, if you want to devise some algorithms, so automatically data sets are available. You can see different kind of archives like the UCI repository, you can get the data set here, right? After the data set, the second step that is very crucial, that is called data visualization and data exploration. What is that? Because whenever we have a data set, the characteristics and the behavior of the data would be different. So based on the behavior, we can select the model. Generally, whenever we use machine learning, blindly we use a neural network, blindly we use a decision tree, support vector machine. That is not true actually, because we need to see the data, behavior of the data. That behavior of the data is experimented in the data visualization and data explorations. Based on the characteristics of the data, then we can select one of the models. But keep in mind again, so you need to have complete idea about all the models. Only then you can select, otherwise you cannot select. But one thing here, this is still a challenging problem in machine learning and data mining community. That is called model selection. Whenever we have a machine learning task, which model should be used so that we can get optimal results? That is the challenging problem to the machine learning and data mining community. So you can work on that. So keep in mind for the model selection, this data visualization and data exploration is very much crucial. So after this data visualization and exploration, then we come here. Then we come here. So here what, how many tasks we are having here. So just we have pointed out here 3 tasks, and these tasks are handling missing values, crossing down problem, and feature selection. But keep in mind here also we can have more tasks based on the machine learning paradigm. But keep in mind the conventional paradigm, if you talk about the neural network, decision tree, support function machine. So for those conventional paradigms, we can use these people processing tasks. But there are some other conventional, different kind of say paradigms. In those paradigms, we can use different kind of say stages. For an example, say feature weighting. This part is not given here. Just we have written feature selection. So here in this context, we're going to talk about handling missing values, classing downs problem, feature selection, and then so how to model and how to evaluate the machine learning algorithms. Then we are looking at that. So come here, the first one. The first one is called handling missing values. What is that actually to do? If we handle, then what we get the benefit? Actually, it improves. If we handle the missing values, improves the quality of the training. If it improves the quality of the training, then quality of the models, quality of the system becomes better. If the quality of the system becomes, means we get the higher accuracy. So keep in mind, whenever we have the missing values, the treatment of the missing values is very much essential. Now the question is how we can create the missing values. See here, you can understand the meaning of the missing values. See, we have this vector, independent parameters, independent parameters. Similarly, for this pattern we're having. Similarly, for this pattern we're having. Now see this pattern here, this hardware is missing here, right? So this is missing values now. So if we have this kind of missing values, then the quality of the training won't be better. So the objective is to give certain kind of treatment here so that the quality of the training can be better. So how we can give, how we can treat it? Yes, we can treat it. There are number of ways. So 2 popular ways that here, there are deletion and data imputations. So coming to first one, the deletion. Deletion, different kind of deletion methods are here. The deleting rows, deleting columns, pairwise deletion. What is that? If we deleting rows, means what we're having one missing values here, right? So what we can do? We can delete the whole rows. So if we delete the whole rows, then the size of the data becomes like this. So if so, then the size of the data sets becomes less. So this kind of deletion method can be used if the size of the data set is huge. If the size of the data set is less, then we should not delete the rows, because we know that if the size of the data set is very huge, then the generalization capability of the algorithm which is trained here is more. So if we do deleting rows, then this kind of say refined data set will get. And now if we do which one, deleting columns now. So deleting columns, yeah, if you see these columns, this is missing values, missing values, missing values, many missing values are there, right? So we're looking at in 3 patterns the missing values are there. Here. In most of the cases we're looking, missing values are there. So it is better now to delete the whole column. Because now if we delete the rows, one row, 2 row, 3 rows, so we're deleting number of rows here in that way. So it is better we can delete the whole column. So if you use this column, now the data set becomes like that. So keep in mind, if in a particular column, if you're having number of missing values, then it is wiser to delete the whole column, not the rows. And then again, we're having here, so this one, yeah. Up to here, we talked about the deletion, and the pairwise I'm not talking about. Pairwise is a very simple concept because it is having some missing values. So during the analysis, what we can do, we can omit this one and we can analyze the data. Fine, that is called pairwise, treatment by deleting the data. And after deletions, we're having the data imputation. Data imputation means what? It is talking about impute the data, means artificially we need to create the data. So we had here one missing values, right? So if we have a missing values here, now we're not going to delete the data, we're going to impute the data. We're going to artificially create the data. For the data imputations, we're having number of ways here. These are the ways: mean, median, mode, linear interpolation, linear regression, KNN, and different machine learning techniques can be used in a wider way to treat here. So you can develop certain kind of algorithms for data imputations here, keep in mind. So now if we use a mean, so how the mean can be used? We find, apart from this one, we can find the mean of all the values of this column. So mean is 67, that's a 67 can be used here if you use a mean for data imputation, right? And here, if you use, say, the values are, say, categorical values, right? Even if it can be continuous, there is no problem. So now say the values are categorical and this is the missing value. So now we can use a KNN concept. So if we use the KNN concept, the value of K should be given, say the value of K is 4 here. So 4 means 4 nearest neighbor, this, and this. But we can use the majority of voting. So we have yes, no, yes, yes. So the value will be here, yes. So yes can be given. In that way, we can do the data imputations. But keep in mind, it is not suggested that you impute the data. Impute the data means what? You are creating the data artificially. That's why it is called data imputation. So imputation is not good habit. So now you have your questions in a data set. How much data imputation should be done? The recommendation is none. But if you have to do, because you have no way, then it is wiser to do up to 3 to 5%, not more than 5% to do the data imputation here. Now, one question you may have in your mind that why those missing values actually in the data set? We can have a data set so that we will not have any missing values. No, when we collect the data, because we do survey, only then we can collect the data, or from the experimentation lab or research lab, we collect the data. So during the survey, say you are having a questions the age of a girl in the survey. So most of the girls, they are reluctant to give their age actually. So in that, in the age column, we can have number of missing values. Similarly, if you ask the salary of a boy and who are earning huge salary, they are not telling you the truth. So in that way, again, we may not get the value. And also in the research lab, when the instructor puts the values, sometimes they miss some kind of values. So in that way, actually, these missing values are generated. So if we have the missing values, the summary is that the missing values are actually tricky actually. After missing values, we're having here, and that problem is called class imbalance problem. What is that actually? We need to understand. And if we have class imbalance, then what can be the problem? We need to understand. So if, say, we're having a binary classification problem, so we are having two classes, one black dots and some blue dots here. If you see the number of blue dots is 10 and number of black dots is 20. So in this case, the number of black dot is more and blue dot is less. So this kind of data set or this kind of problem is a linear problem, but this is also called class imbalance problem because one class overpowers another class. If class imbalance problem is there, then what is the problem? The problem is here biases towards the majority class. So whenever one model is trained in the imbalance class, imbalance problem or imbalance data set, whenever new pattern comes, then the classifier will have a tendency that the new class has to be classified into the majority class. That's the problem. So keep in mind, whenever we have an imbalance data set, then making one good classifier is really challenging because it biases towards the majority class. And what we can do? We have number of solutions for that, and these are the solutions. So three popular methods are here: the sampling, and one is called sampling, algorithmic approach. These are the approaches, sorry, not method, approach. Sampling approach, algorithmic approach, and sampling approach. In sampling, we're having two kind of approaches. One is called undersampling, another one is called oversampling. What is undersampling? Undersampling reduces the majority class instances. In this problem, if you use the undersampling, somehow you reduce the number of black dots from here. That is called undersampling. Now the question is how we can remove those black dots. Now to remove those black dots, we're having number of methods. Methods means we're having number of algorithms. First one is RUS, random undersampling, but it is having certain kind of problem because it can remove, because this is random undersampling, it randomly picks the data from the majority patterns and throw them out. if we do this kind of thing, then some kind of important informations may be lost. Some kind of data pattern can be important for the class, but that one also can be missed out. So to overcome this MUS, there are a number of algorithms. These are atomic link-based undersampling, condensed nearest neighbor undersampling, and there are different kind of undersampling algorithms are there, and it's a trend. If you want to do research in say, data mining, or you can say data science, so you can look at here. And then this is oversampling. It says what? It increases the minority class, not majority, it's a minority class. So increases means what? We're having 10 blue dots and we're having 20 black dots. So now we can increase the number of blue dots here so that at least we can balance them. So here we have 20, so we can make it 18 or 19 or 17 here. So oversampling signifies increases or increasing the minority class. Now there are different kind of approach algorithms. The first one is called ROS. This is random oversampling. So randomly, if you oversample again, there is a problem that we can create some kind of synthetic pattern which are not say meaningful. Now to overcome this one, we're having different kind of algorithms, and these are the state of art algorithm in oversampling. And these algorithms are small, synthetic minority oversampling technique, borderline small, safe level small. These are the state of art. So if you want to work on oversampling, you can work on those algorithms, because all these algorithms are having again certain kind of drawbacks. And then after this sampling, we have algorithmic approach. This is algorithmic approach. Actually, in algorithmic approach, what it does actually, it changes the cost function, and it maximizes the misclassification cost of the minority class. What actually the meaning of that? Because during training, whenever the model is trained, each instance is given to the model and the model is trained. Each instance is given to the model and model is trained. Now, if we talk about this case, if you talk about the blue dots, so how many times the blue dots can be inputted to the model? 10 times. And how many times? This is 20 times. So more number of times this black dot is given here, and this blue dot is given less number of times. So it is wiser whenever we take one minority pattern, and whatever misclassification is done, the misclassification cost can be doubled, because this number of black dot is doubled or twice than the blue dots. So if it gets once, it gets chances how many times? Twice. So whenever one blue dot misclassified, then the misclassification cost can be doubled. If it is double, then somehow we can say the classifier is a bit balanced. So in that way, if we do, that is called actually algorithmic approach. And one of the most popular algorithmic approach is cost-sensitive neural network. Because in neural network, whenever we do, it takes that the data set is balanced. So with it can be minority instance, it can be majority instance. It gives an equal misclassification cost. But keep in mind, we can find what is the ratio of the majority and minority. According to that, the misclassification cost can be changed, and then the algorithm is called cost-sensitive neural network. Under the final approach, that is ensembling approach. Already you know ensembling is we are putting their number of classifiers, generally the swap classifiers together. And using the ensembling approach also, we can sort out this problem. And the popular ensembling approach to sort out these problems are smooth boost, RAS boost. So you can, because now people are working in ensembling, this is a trend. Using ensembling, we can classify. Using ensembling, we can do also, we can treat also class imbalance problems. So you can work here also. And after that, the issue that is related here, that is called feature selection. But I'm going to talk about in the feature selection, because here number of things are there. Feature also extraction is there. I'm not going to talk about feature extraction, only feature selection. What is that actually? Feature selection is talking about if you're having say 1, 2, 3, 4, 4 features, you're independent and the class is only one Y. 1, 2, 3, 4 and Y. Now say, now to find this class, it is found that this feature doesn't have any impact. This one doesn't, S doesn't have any impact. So if it doesn't have any impact, then we shouldn't keep that. It becomes an irrelevant feature. That is irrelevant feature. So if you're having say irrelevant feature, then it should be removed. So if we remove this one, then what is the benefit of the model? because we're looking for the benefit of the model. So if we remove irrelevant features, features can be done in two ways, and irrelevant and redundant. So initially I'm talking about the irrelevant features. If it is irrelevant, then we can remove this one. So if we remove irrelevant features and redundant features, then generally we get two benefits. And these benefits are reduces cost and then increases accuracy. Reduces cost means what? As we're looking here, the size of the data is very small and number of attributes is very less. But keep in mind, if you talk about social networking data, if we talk about GIS data, if we talk about DNA microarray data, a huge number of attributes will be there. In microarray, this DNA microarray data is having around how many genes? 450,000 genes. So that number of attributes are having. So if you talk about the textual data, if you find the keywords, number of keywords for a particular text can be thousand and thousand. So in that case, actually the dimensions of the data becomes very higher and very huge. So in that case, actually, if you remove some of the data around say features, say 500 features from say 20 lakh data samples, then if you see the space which is reduced is very huge. If the space, if the size of the data is very less, and if the size of the data is say decreased, or if we can say diminish the size of the data, then the size of the memory is less. So if the size of the memory is less, then which one? The memory requirement would be less. At the same time, the algorithm becomes much more faster. In that way, we can say it reduces the cost and increases the accuracy. Sometimes we can have certain kind of features, and the features doesn't have any impact. The impact of the features can be negative in a particular problem. So if we have some features whose impact is negative, whose relevance is very less, irrelevant features, due to those features, sometimes it decreases the accuracy. So if we can find those kind of features, and if we can remove those kind of features, then the accuracy increases. And again, one term is there in machine learning that is called picking effect. Picking effect says that actually, when we have a data set, and if we increase the number of features in a sample, and at the same time, if we increase the size of the data set, generally, the accuracy of the system, accuracy of the machine learning algorithm increases. We are increasing features, we are increasing data size, increasing the accuracy. But keep in mind, at a certain point, increasing, and we are reaching to a level, to a point. After that point, if we increase the number of features, then the performance of the system doesn't increase, rather the performance decreases. At that point, and that effect is called picking effect. So if we do the feature selection, it reduces the cost of dimensionality. That is called cost of dimensionality. If we have a limited size of data set, and if we increase the dimensions, increase the number of features, at a certain point, the performance drops. So it is wiser to remove the features which are irrelevant, so that we can select a subset of the features, so the performance of the system can be improved. Now the questions: how we can select the features? There are different kind of methods. Different kind of methods are there by which we can select the features. These are the methods, and I'm going to tell you which are the popular. And the first one is exhaustive search. This is the method. This is not an approach. This is a method. Keep in mind, method. Method is talking about an algorithm. It's step by step how we are doing. And if we talk about approach, it is talking about the way in what we were going to do. And this method is the algorithm: exhaustive search, a branch and bound search, selection of best individual features, sequential forward selection. These are the methods. So if we use the exhaustive search, then the algorithm becomes a NP-hard problem. The problem becomes NP-hard problem. Exhaustive means what? We need to use all the pairs, all the subsets. So which subset is better? That's the subset should be taken. So if we explore all the subsets, and now if the number of features is more around say 30, and we want to take say 12, then we cannot take it. The number of subsets would be more than millions. So if we analyze more than million subsets to find which one is the best subset to select the features, then this problem can be not practical, or this problem becomes an intractable problem. And then if it is intractable problem, then that problem is NP-hard problem. Now to overcome this NP-hard problem, then the second one comes, that is called branch and bound search. And here we can set some threshold. Based on threshold, if the performance is low, we can have certain kind of assumptions here. Then we ignore the start and we can look for the next one. In that way, somehow we can reduce the time complexity here. And after that, again, we have selection of the best individual features. And here we have some problems. Whenever we do or we select the features using best individual features, means all the features are individually experimented or analyzed. And then we can find the performance of each features individually. And then based on how many features we need, and based on that we can pick up the number of features from there. But one thing is missing here, as the features are analyzed individually, so the interrelationship between the features are missing here. Because if we talk about here this BP, heartbeat, weight, this must have certain kind of interrelationship. But whenever we experiment it individually, this, then this interrelationship is missed. So this is not a good way to select the features. Then we have the sequential forward selection. And here what we do actually, we actually forward selection, that will start with say empty set. We pick one, then again we see which one is the best out of two. We take this one, then out of this say this and this. Now these two are best. Now two are left, this and this. Out of this and this, which one is the best? Then this one can be taken here. In that way, actually, this sequential forward selection works. But here is the problem that is called actually nesting effect. So is that effect actually once a feature is selected, say initial started with BP and heartbeat is selected. Once a feature is selected, that feature cannot be dropped. That problem is called nesting effect, because when you analyze this and this, then heartbeat seems to be important. But keep in mind, whenever we'll have this one cannot be, or this one doesn't seem to be important. Even if it doesn't seem to be important, we cannot drop it. That is for nesting effect. Similarly, that nesting effect is also associated with sequential backward selection. I'm not going to talk about it because these are the math algorithms, secret algorithms, and I cannot cover up the whole part. Then because this sequential forward and sequential backward are having the problem that is called nesting effect, and this nesting effect is overcome using sequential floating forward selection, sequential floating forward selection, and using sequential floating backward selection. And again, it has the way how to use those things. Not talking here. So if you talk about the methods which are with the state of art method, these methods, sequential floating forward selection or sequential floating backward selection. These are the algorithms, keep in mind. Now, in this algorithm, we need to measure certain criteria, need to measure certain constraints. Now, how we measure those constraints, these are called actually approach. So if you talk about the feature selection, if we talk about the approaches, basically, there are two approaches. One is called filter approach, another one is called rapid approach. But in most of that, in some articles, in the recent articles, now the approaches are categorized into 4 categories, and these categories are filter approach, wrapper approach, then hybrid approach. The hybrid approach means using filter, then wrapper, and then embedded approach. So just I'm discussing briefly what is filter actually. Filter approach. Filter approach is talking about the statistics of the data, statistics of the or mathematics of the you can say mathematics of the feature. So mathematically and statistically, we're trying to find out how the feature is important. So we are looking some mathematics, we are looking importance, we are doing certain kind of statistical operations on that. If we do, then that is called filter approach. In filter approach, we are having different kind of measures. For example, Pearson correlation measure, right? Cosine similarity we can find. Feature score, Fisher score we can do. Information gain we can do. Mutual informations we can do. Within those things we can find whether the features are, which features are most important. If the feature score is more, then you can say the feature is more important. Similarly, if the information gain for a particular feature is more, then we can say the feature is more important. So whenever we find the information gain or mutual informations, we need to do certain kind of mathematics. We need to do certain kind of statistics to find the gain or the mutual informations. If we do Or if you follow that approach is called filter approach. And if you talk about the wrapper approach is not talking about any statistics. It is solely depend on machine learning algorithms. The classic learning algorithms are applied and looks whether the feature is important or not based on the accuracy. So wrapper approach is totally black box in nature, but keep in mind it is computationally expensive than filter approach, and the accuracy of the wrapper approach is better than filter approach. So that is filter and wrapper approach. Now talking about, say, now this pre-processing part is done here. So we have done all the pre-processing kind of things because we selected number, we have selected which subset is best. For an example here, so this feature is not good, so this feature can be dropped. Then these three features can be taken for the classification. Fine. So initially we are talking about the classification, but I'm going to cover all the classic means the supervised, unsupervised, and also reinforcement. So if it is say classification, that after selecting this feature set, now we need to evaluate the model, because modeling part is up to here. This is also part of modeling, right? So up to here, the different kind of issues are sorted out. So whichever issues we had, we sorted out, and now we got the final data set and a final subset of features. Using those features now, say for the sake of simplicity, it is a classification problem. We got all the feature subset and we have the classifications now. So they're coming here now. So now we need to model the algorithm now. How we can model now? So we have to train the model, because we now got the data set and the refined data set here. So for the training, actually, for supervised learning, we have the popular method that is called hold out method. Many of us actually use the hold out method. What is that actually? Generally, whenever we have a data set, the data set is partitioned into two parts. Say it can be 80-20 or it can be 70-30. So 80% for training and 20% for testing, or 70% for training and 30% for training. So if we do 70% for training and 30% for testing, so if we do like that, that is called hold and out method. But keep in mind, sometimes the whole data set is partitioned into three partitions. One part can be training, another validation, and then testing. And this validation part is kept if we need to tune the model parameters more, or if we want to validate whether the model parameters which are trained, which are found using training, whether they are working or not. If they are not working, still we can improve or we can optimize the value. Then we can have one validation set. Using the validation set, we can check it. If it doesn't work as per the expectation, then we can change it with the validation data sets. So after doing this one, then the test set can be given here to test the model. But if we use this hold and out method, this hold and out method suffers extremely for imbalanced data. So if we have an imbalanced data set, then if we use hold and out method, that is not acceptable. Using this one, if you find the accuracy of a model, then it doesn't work actually. It is not accepted in the research community. Then what we need to do? The most popular, say this method is called K-fold cross-validation method during training. So if we do the training in K-fold cross-validation, it is accepted. In K-fold cross-validation, again, we have two kind of things: tenfold cross-validation, and one is called leave out one cross-validation. I'm not going to talk about this one. I'm going to talk about this one. Tenfold cross-validation. It means what? So if we have a data set, the whole data set is partitioned into 10 folds. For an example, for the sake of simplicity, we have a data set, and size of the data set is 100. 100 data is there. 1 to 100, 1 to 10, 11 to 20, 21 to 30, like that. So we have 10 folds here. What generally we do? That's the problem. Here, what we do generally in the first iteration, in the first fold, we keep 1 to 90 for training. All those for training, right? So model is now trained. After training, now this part 91 to this 100, this pattern is given here to test how the model works. So now we can record the accuracy. Now in the second iteration, we keep this 71 to 80, then again 91 to 100. We keep in the training. And here this part is taken back for testing. So we train the model, test with a different fold now, this fold. Similarly, we can train with different folds now, and this fold is taken for the test bed, for testing the model. Now again, we can find the testing equation and we can record it. Similarly, we can do for this fold. Similarly, we can do for this fold. Similarly, we can do for this fold. Similarly, this. For 10 folds, we had 10 times. We trained with 90% data. Folds are different. Folds are different, right? So 10 times we can train the model and 10 times we can find the accuracy, testing accuracy. But keep in mind here, if we see carefully, then we can see that the model is trained with say different with replacement, different kind of say data samples. But the model is tested with all the data which are available in the data set. So now the accuracy, whichever we're getting from here, that one becomes more generalized. Even if the data is not uniformly distributed, even if data is imbalanced, it doesn't have any effect now because the model is tested with all the test patterns, all the data patterns. So now the test pattern becomes the whole data set. So it doesn't have any impact. That's why this tenfold cross validation is universally accepted. So whenever you do such kind of research work, if you do tenfold, or if the journal is very good, if you don't do tenfold cross validation, the journal generally doesn't accept the paper. So this is careful cross validation method for modeling, for training the model. So one way more is here that is called bootstrapping. What is that? In bootstrapping, it uses simple random sampling with replacement. This technique is used here. I'm going to tell you what is that actually. Why? When this bootstrapping is used, when the size of the data set is very small, then to train the model or test the model, we need to use the bootstrapping. And here, keep in mind, we can make any possible number of the training and testing. That's why this called training and testing is unlimited. What is that actually? See here with an example. Say in the data set we're having 10 data only, P1 to P2, right? And keep in mind now we can create different data samples. How many n number of whichever we want, 100, 200, whatever we want. With the different combinations, we can make the data set with the same size. How many we're having? 10. So keep in mind, we make example 1, P1, P1, P1. How many times we have taken P1? Because this is with repetition, with replacement, right? So here P1, P1 we have taken 3 times, so P2 to P8. So this is one sample. But keep in mind here the number of samples is 10. Similarly here we have P1, P1 2 times, P2, P2 2 times, and P5 to 10. Again one sample is created here. Again keep in mind here the total number of samples is 10. Here also total number of samples is 10. So in that way, with the different permutation and combinations, right, with replacement, we can create n number of samples. Now we're having n number of samples. Now we can do n number of testing and training and testing. And finally, the testing can be the average testing of all the samples. So that method is called bootstrapping method. But keep in mind, if the database size is very small, then generally we use this method. So we have seen here 3 popular kinds of training methods, training strategies, right? So after training, we have to validate the model. Means whether the model is working or not, we need to check. That is called evaluation of the model. So for evaluation, we have number of performance measures. As I have given here all the performance measures which are for supervised learning. We're going to talk about unsupervised and reinforcement also. So here we have all the models. These models, these are especially for the evaluation or performance measure for the classification, right? So we have a recall, precision, accuracy, false negative rate, F measure, AUC card, also ROC card is there, MCC, and Matthews correlation coefficient. It is talking about correlation coefficients. So we can have many more, right? But if these are the popular list. If we use this one, then it is sufficient, I think. These are the parametric tests. We can have some non-parametric tests because whenever the sample is not uniformly distributed, if the data set is not uniformly distributed, if you do only the parametric test, then it is not accepted. Then we need to do some hypothesis testing. That is called non-parametric test. So Wilcoxon's ransom test, fragment test, different kind of tests are there. So here we have the recall, precision, accuracy, false visual. So all those performance measures we can find using this confusion matrix. Within the confusion, this is the confusion matrix for the binary classification problem. We can make for 3 classification, 4 classification, we can make. So here for the for easy understanding, we have here the confusion matrix of 2 into 2. So recall is talking about what? Recall is talking about how much positive pattern you can recall. That is called recall. See here, TP by TP plus FM. True positive bar plus false negative. Because actually this is positive, right? So, and then in the prediction, it becomes false negative. So that's why it's called recall. Recall, try to understand. Recall means how much it can recall. Which can recall? What kind of pattern it can recall? Means how much positive pattern it can recall. It can recall. That is called recall. So that's the equation. So if you remember in that way, then you cannot forget. So how much it can recall the positive patterns. And now we have a precision. Precision means we got the positive patterns. How precise the result is actually. We got the positive patterns. All positive are not real positive. How many percentage is the real positive? That is called precision. Means how precise the true positive are. That's why it is written here, true positive by true positive plus false positive here, written here. Now similarly we can find model accuracy. This is whole accuracy. Average accuracy we can find here, total accuracy in that using this equation. Now for false negative rate we have this, because false negative rate is using to find the ROC curve actually. So, and then we have this one F measure. This is the harmonic mean. Harmonic mean is nothing. Harmonic mean is a kind of average. Pythagorean average is called harmonic mean. So we're finding the average of precision we call here. So generally, in most of the cases, in the research paper, the value of F measure is generally seen. That if your F measure is good, then it is believed that your precision and recall both are good, because this is the average of precision and recall. So that's why F measure is generally looked upon. And in the research paper for classification problem and the supervised problem. And also we have different area on the curve. Matthews correlation coefficient is a kind of coefficients. This coefficient is a very popular measure for the binary classification problem. So if you try to understand, it's a kind of coefficient. That's why the value say runs between the ranges between -1 to +1. If the value is +1 means it's very good. If -1 is very bad, like that. Fine. So these are the performance measures for the supervised learning, and if the model is the classification model. Now in the supervised learning, if the model is a regression model, then the performance is measured by R squared. In R squared, generally we need SST and SSP, sum square error and sum square total. Using that one we do. Fine. And if we talk about the unsupervised learning, in unsupervised learning, two tasks are there. One is called clustering, another one is called association reminder. In the clustering, we can measure the performances using two measures, two popular measures. There can be number of measures, but two popular measures are there. One is called Silchar coefficient or Silchar index, and another one is called purity. I didn't include here all those things, purity. And if we talk about the association rule mining, the performance of the association rule mining is found using supporting error. In that way, we can model and then we can evaluate once a machine learning model. So here, most of the things we talked about for a supervised learning algorithm, that is spatial classification algorithm, right? So we talked about these are the small issues, whatever we had. Yes, I briefly discussed about all the issues. The issues can be linear, can be say extended hours and hours. I did not discuss all those things. Now, one of the machine learning classifier, which is very popular, I'm going to talk about, and talk about mathematical part. If you have any problem in the mathematical part, you can ask me, you can discuss, we can discuss here, and that is the decision tree. Whatever in the presentation, it is written decision tree and random forest, and I thought that is not possible to cover up decision tree and random forest. Thus, I have taken here the decision tree only. So decision tree produces what actually already we know. Decision tree is a supervised learning, and it generally does, most probably does the classification task. But keep in mind, it also can do a regression, because finally we have a version card, the classification and regression. That's a version of decision tree. So decision tree can work on categorical data and also can work on the numerical data, the continuous data. It can work for the classification problem. It can also work for a regression problem. That is not the main thing. The main thing is that whenever we find results, whenever we solve certain kind of problems, what do we want? Do you want the black box output, or do we want certain kind of justification or the transparent rule, is how the decision is being taken? So if we want to have a transparent rule, is how the decision is being taken. If we want to see, in that case, is the decision trees will be used. For an example, I'm talking here for an applications. I have number of applications, number of students are working on that, but I'm going to talk about one of the application. For an example, you apply for a loan. Nowadays in banks, there is an automatic software, automatic algorithm, machine learning algorithm, which decides whether you are eligible for the loan or not. So for example, you are not eligible for the loan, no. But in our country, there is no legal issue. But keep in mind, in most of the developed countries, like France, like the UK, if the loan is not granted, if it is rejected, then the justification is to be given. Without that, that one becomes a legal issue. So then in that case, if you have a black box decision, then you cannot say anything. So in such cases, if you have a transparent decision, these are the criteria. Transparent means what? If we have a kind of rule, if this attribute greater than this, if this attribute less than this, then this is yes. If the condition is this, then this is no. If the whole rule is given, then we can say that is transparent rule. So keep in mind, decision tree is one of the data mining and the machine learning tool which produces a transparent decision. So the domains or the area or the applications where the transparent decision is required, in that case is the decision tree can be used. So this is one of the things. And the second thing is that in machine learning, one term is there that is called compactness. Compactness. But decision tree provides compactness. It means what? Yes, to train a decision tree, the database size is very big. To train a decision tree, a lot of computation is required. But keep in mind, once it is trained, then it finds only set of rules. It can be 2, 3, or 4 rules only. So whenever some new pattern comes, you don't need to train the decision tree once again. Just you need to see the rules. If you see the rules, according to the rules, you can decide whether this pattern belongs to which category or what should be the value of this pattern. So that is called compactness. Yes, during training it takes time, but once it is trained, then the whole effort becomes very less. Then the whole system becomes very compact because we're having all these few rules only. So this, if we want to achieve compactness, the compactness can be achieved using the decision tree. So we're now going to talk about the decision tree, how to make this decision tree. We have a problem here. See the problem carefully, then you can understand everything one by one. So we're having how many patterns here? T1 to T8. We have 8 patterns. How many attributes we're having here? 1, 2, 3. 3 attributes we're having here. How many classes are here? 2 classes. One is student, 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 and professor, professor. 3 professors are there and 5 students are there. This is a simple problem. And we're having 3 attributes, habit, age, and footwear. Using these 3 attributes, we're going to classify now. Yes, now we're going to use which one? Decision tree. So we have this problem, right? Start with this one, habit. Say, we have taken habit here. Say. So if we take habit, then habit has how many values? Gabby and Y, 2 different values. That's why the whole training set would be split into 2 subsets here. So one for Gabby, so T1, T1 here, T2, T2 here. For Gabby, T3, T3 here, and then T5 Gabby, T5 here, and T7 is here, right? And all other are the quiet, T4, T6, and T8 only. We have 3 here. So habit is experimented here, explore here. So which are left now? Eat and footwear. So we can take one of them. So let's say the eat is taken here. So now if you see the eat, how many different values are there for it? 3. That's why it creates 3 different subsets from this main set. See here, baked, 1 value, roasted, another value, fried, another value. As you are having 3 different values, that's why it segregates the main set into 3 subsets. So one for baked, another for this, another for this. So in baked, you see that we have key. If you see the baked from here, T1, T2, T3, and T5. From here, we are now applying this one. It's so out of these 5 patterns, if we use the if and value is baked, then we can say which patterns are applicable. T1 and T3. See, T1 is baked, T3 which one? Baked. Accordingly, this we make it. And one thing can be observed here. The class of T1 and T3 both are student. That's why it is labeled. The node is labeled. Whenever all the pattern belongs to same class, then the node is labeled. And see here now, roasting. So how many out of this 5? Only one T2. So, and one pattern is there. Obviously, the class, what do we say, defined here. The class is P, professor. That's why it's given here. Now, how many are left? Left T5 and T7 left. You see the T5, the category of T5 is student and T7 is professors. As the categories are different, that's why still they are not solved. This node is not solved. So still we need to apply, right? Similarly, we can apply here. Similarly, we can apply here for each. Again, we can create similarly. And again, it's for fried. All the values are doesn't belong to the same class. One thing should be pointed out here. If we have T4, T6, and T8 here, if we roasted, if the value of it is roasted, then if you see T4, not roasted, fried, T6, baked, not roasted, T8, fried, not roasted. So none of them is roasted. So if so, then it is empty set. But if some new parent comes here, then it cannot be set. That's why the question is question mark, right? So if you're working in decision tree, so you can devise certain kind of protocols here so that you can publish some paper if you work in decision tree. So if it is baked, then it comes student. And here, how many we're having? T4 and T8. T4 and T4 is professor, T8 is student. So 2 classes are there, not same class. As they are not, as all the patterns do not belong to same class, that's why we need to apply again some attributes here. So if we apply the attributes, yeah, one pattern is here, one pattern is here. So one pattern, obviously the class is same, Similarly, here the class is same, So in that way, in footwear actually we had 2, T4 and T8, and now the clogs and sandals. Accordingly, we can see here. I'm not going to too much here. So just one edit here. So for footwear, how many left? T4 and T8. T4 and T8. And what we had? The footwear. If the footwear is sandals, we have sandal. Then what? Professor. The professor T4. Similarly, if it is clog, then it's student. Clog is student. Similarly, we did here. In that way, the decision tree is created. So keep in mind here, but we don't know right now which attributes should be taken first and what combination of the attributes should be taken on the left side, what combination of the attributes should be taken on the right hand side. We don't know. We have taken arbitrarily, right? So we created one decision tree here. Similarly, by changing the order of the attributes, we can make one more decision tree. Again, by changing the order of the attributes, we can make another decision tree. We can make another decision tree by changing only the order of the attributes. Again, we're making how many? We're making 8 here. That is not finished. Still, we can make the different decision trees. So now it's a big question. If you have the different decision trees for a problem that is not justified, then what can be the problems for the different decision trees? The problems are here. Say we are having R1, R2, R3, and R4, 4 test patterns. Already the model is trained. We use 8 decision trees. We made 8 decision trees, and 8 decision trees are different. The rules are different. Now we're going to check the recall pattern R1, R2, and R3, R4. So whenever R1 is applied, then all the decision tree classify it to a student class. Now, if R2 test pattern is given, some of the decision tree classified to professor and some of the decision tree rejected. And if it is R3, then some of the decision tree classified to students and some of the decision tree classified to professor. And if it is R4, then some of them classified to student and some of them classified to professor. See here, the output is not consistent. We're having different decision trees and the decisions are different. So if we have a different decision trees and inconsistent output, then it is not accepted. So we must have some unified way to create a decision tree, right? So now we're going to make see the unified way by which the decision tree can be created. So how the decision tree can be created? What is the logic on that? Because we have seen different kind of attributes are applied and then the decision trees are created. Now our objective is to select the attribute which one is the most important. How we can select which one is the most important? The attribute which has the most discrimination power, discrimination capability of the classes. That attribute is chosen or that attribute is treated as the most important. Now the question in decision tree, how we can find which one is having the most discrimination ability. In decision tree, generally that discrimination ability is found using information gain. If the attribute is having the highest information gain, then we can say that attribute is having highest importance and that attribute is most important. So keep in mind in decision tree we are going to find out the information gain, but keep in mind in information gain there is certain problem and later it is defined as a ratio of information gain, because earlier using information gain the decision tree is created and that decision tree is called ID tree, iterative dichotomizer. But information gain is having certain kind of drawback. I'll show you one by one. Then the information gain or the information of the activity start at a ratio of information gain, then it becomes C4.5. Fine. And one thing that should be noted here, the difference between ID3 and C4.5 is that ID3 is applicable for categorical data. But keep in mind this one, this C4.5 is applicable for categorical data as well as continuous data. There is no problem. And again, in ID3, there is no concept of pruning. I'll tell you what is the advantage of pruning. But in C4.5, there is a concept of pruning. But here it does pre-pruning. But in CART, it does a post-pruning. I'll tell you. So in the ratio of information gain, our objective is to find the gain in information gain of the attribute. So how we can find this one in decision tree? In decision tree, generally, we use the concept of entropy. What is entropy? We need to understand. Entropy is the reverse of confidence. If the confidence is more, entropy is less. So if it's the entropy is more means, it is the reverse of means entropy is more means what? Confidence less. If the confidence is more, entropy is less. Try to understand. Fine. So now, based on the concept of entropy, just one term you just remember, entropy is the reverse of confidence, the reverse of knowledge. So if knowledge is more, the entropy is less. So how we're going to do, what is the philosophy of that? Here you see. So initially we're going to find the entropy of set V0. That's the entropy of the set V0 means entropy to classify is the information required to classify a pattern into one of the classes. Into set V0. One of the classes. The information required means the entropy required to classify a pattern into one of the classes. So we need to find the entropy of set V0 here. Just you try to understand that way, in a simple way, not take all the technical terms. If I tell you all the technical terms, then it becomes a bit difficult to understand. So entropy of set V0 we are finding, right? Entropy means the information required. So we're finding entropy of set V0. Now we are applying one attribute here, A. Now say A is a attribute and A divides this set into two subsets, V1 and V2. So whenever A is applied, then the confidence of the classification should be improved because one attribute is applied here now. So now the whole entropy of this set and this set should be less than this one because now attribute A is applied here. So whenever one attribute is applied, some kind of confidence would be grown here. So now if you find the entropy of this set and entropy of this set and finally sum up, merge it. So if you find the final entropy, this final entropy should be less than this entropy because entropy is the reverse of confidence. So whenever one attribute is applied here, the confidence should be more. So when one attribute is applied here, then we can find the entropy of this set and this set and then total entropy of this level. And finally, we can find the difference between this entropy and this merge entropy. And that difference is called information gain for attribute A. That one we're going to find now. That one we're going to find, but we need to do these calculations. Now, seeing the data set, we're having m number of classes, where m greater than equals to 1. And this is one of the nomenclature, k comma I. It talks about the number of patterns belongs to class ck inside vi. And data is talking about all the patterns inside vi. So if you talk about vi, because we have considered how many classes are there, m number of classes in vi. So now, if you talk about Zi, means the total patterns of this set, the total set can be any of the classes. That's why it's a summation of k equals to 1 to m and this one. So Zi is talking about the total number of patterns of set vi. And now the probability that a pattern in V0 belongs to class ck is. It's talking about what is the probability that a pattern belongs to class ck in set V0. This is the probability because it talks about what? It talks about number of patterns of class ck in set V0 by total number of patterns. So now you find this probability, and this probability is called prior probability. That is called prior probability. So now, for an example, you find this probability for class student. So how we can calculate 1, 2, 3, 4, 5. 5 by total how many? 8. So 5 by 8. So this is prior probability. If now this prior probability is more, then the confidence is more that if we pick one of the pattern from set V0, it belongs to class ck. If the prior probability is more, then the confidence is more that if we pick randomly one of the patterns from set V0, then it belongs to class ck. Fine. Now, if this confidence is more, then the entropy should be less. This entropy is called actually the information required to classify. Now, the information required, try to understand here, the information required to classify a pattern in V0 into class ck, because already we have seen that this is more. The probability that a pattern belongs to class ck is more. That's why the information required, now the information required to classify a pattern in V0 into the class ck means the information required that a class belongs to ck will be less. How we can make this one? Because now if this one is more, now we have to make this one less. So how this one can be done? This one can be done by negative log, because negative logarithm has the reverse characteristics. If the values becomes high, then actual value becomes low. So if this becomes high, then if we make minus log this part, then it becomes less. So here we can get, if this is the prior probability, then entropy for this class is this. For this class, for class ck is this. Now we got the entropy for one class, and this is that. And keep in mind how many classes are here? M number of classes are here. So now we need to find the entropy of all m number of classes. So that's what we have done here, m number of classes. K equals to 1, 2. This, try to understand here, we are going to find the entropy that is called weighted entropy. That is called weighted average information required. Entropy means information required already talked about. So the weighted average information required to classify a pattern inside V0 into one of m classes is expressed as, means now we're finding the entropy for all m classes, not one classes, all m classes. That's why it is summation k equals to 1 to m, and this is the weight. This is the weight of a class. This is the weight, because if it is a student, the weight is 5 by 8. If it is professor, the weight is 3 by 8, and then this is the entropy. So now the whole entropy, this whole entropy, this I V0 is called the entropy of set V0. So now we got the entropy of this one. Simply we got the entropy. Similarly, we can find the entropy of this one, right? So similarly for say V0, so V1, so we can find the entropy of this one. But keep in mind, we need to find the entropy of all the subsets, not one. Say we apply one attribute A here, and attribute A split the set into n number of subsets. That's why we have written here V1 to Vn. And now the weighted informations required means weighted entropy is IA V0 equals to, see here, summation j equals 1 to n. This is weighted. Now weight of this set is how much? 1, 2, 3, 4, 5. 5 by total is how much? 8. 5 by 8. Then we can use this term here. Because already, see here, we need to find the entropy of these, all the sets, n number of subsets, and we are finding the weighted information, weighted entropy. So that's why it becomes summation j equals to 1 to n, and this is the weight. And now for each subset, this one. For each subset, this one. Clear? When j equals to 1, then that is for z1. When j equals to 2, that is for z2. Like that. So if we have 2, then how many terms we can get? 1 and 2 only. So in one term, this plus all the notation of this, and then for this one, for this subset, this, and all the notation of this. So now we got all the entropy here, the entropy of all the subsets here. So this whole, now if we put this equation here, this equation, because this is IVJ. Now if this equation is kept put here, then the equation becomes like this. This is the equation. Now this one is called IVJ, is called entropy of say attribute A for set V0. So now we got the entropy of A. So our objective is to find the entropy of this one, this and this, right? So now we got the entropy of this one, entropy of this one. So now the information gain, that's why it is written here, the gain in information, that is information gain. The gain in information caused by attribute A, splitting set V0 into sets V1 to Vn is GA V0 equals to I V0 minus I V0, because this one is the entropy of this, and this part is the entropy of all this. Now using this one, what we can get? We can get gain in information, right? This is gain in information. So if it is gain in information, then what is the objective of each attribute now? The objective of each attribute is to maximize this gain in attribute. This gain, this information gain need to be maximized now. If this is maximum, then the attribute is the best. So now the endeavor of each attribute is to make this one maximum. So how we can get the maximum this one for each attribute? Because data set we cannot change. That's why the entropy of this one we cannot change. Now if you want to maximize this one, then we need to minimize this one. If this one is 0, then that is maximum. That's why again it becomes a maximization minimization problem, because here the objective is to maximize the value of the gain here. So there is only way if we make it minimum. How we can get a minimum? That is a bias actually. See here, if we have a active, say already we have this problem, this fine. Now say one more attribute is there. This is T1, T2, T3, this one. More attribute we added. Say we have given here attribute names. These are the attribute names. Pattern names. Now say these pattern names are one more feature. Say if these are the more feature, if this pattern name is applied here, then we can see that because none of them is common. None of them is common. This T1, T2, T3, T4, like that. T8. So we can create how many subsets? 1, 2, 3, 4, 5, 6, 7, 8. Just I've kept here 6 due to say paucity of the space. So we can make here 8 subsets. Now we see for each subset, already the pattern is classified. Pattern is already classified. Only one pattern is there. Pattern is classified. Now entropy is 0 here because pattern is already classified. That's why if I talk about information required to classify a pattern into one of the classes, it becomes 0 because all the patterns are now classified. Classified, right? So now if we keep all those things in this equation, then also we can see that this one becomes 0. You can keep the values or directly you can understand from here. Because already all are classified. That's why required information to classify is 0. So I keep here 0. If 0 means this is the most minimum, we cannot make more than that. So now the information gain becomes the highest and maximum. So that's the problem in ID3. In ID3, if we have an attribute which splits the set V0 into number of subsets, then information gain becomes highest. So if we split this set by this name of the training patterns, this subset will be created, and whenever some new pattern comes, the name of the new pattern should be T9, T10, T11. None of them is common. As none of them is common, that's why none of the new pattern will be accepted. All the pattern will be rejected, even if the gain in information is highest, none of the new pattern will be accepted by this decision tree. That is the biasness in ID tree. That's why to overcome from here, one more concept is added, that is called split information. Because as it splits number of subsets, that's why if you find a split information, then the total split information would be more. So I'm not going to, because time is out, I'm not going to talk about all those things in detail, but keep in mind, due to this reason, the split information is required. Because it splits the set into more number of subsets. So now if you calculate the split information, the whole calculation becomes more. The amount of split information becomes more. Finally, these split informations would be the denominator of the whole part. So when I find the ratio of information gain of attribute A, for say V0 is defined as this one gaining information by split informations, because as you are splitting the number of subsets, that's why your gain becomes higher. At the same time, split information becomes also higher. So now to balance the part, these split informations become the denominator of the whole equation. So this is gain as divided by split information. Finally, we get the ratio of information gain. This is the ratio of information gain. So now in this problem, our objective is to find the ratio of information gain for habit, for eat, and footwear. The attribute for which the ratio of information gain is highest, that one will be taken first. So see here, I'm not going to talk about. So see here, we found the entropy here. All the calculations are given here. This is the entropy of say V0. Now if we apply habit, the ratio of information gain of habit, all calculations are given here. So this ratio of information gain for habit will be 0.0047. Now for eats, the ratio of information gain would be 0.3233. Now for footwear, the ratio of information gain would be 0.3642. So now see all the ratio of information gain. So we have habit, eats, and footwear. Which one is the highest? Footwear is the highest. Footwear is the highest. That's why when we make the decision tree, this footwear is taken first, because now this activity is most important and it has the most discrimination ability of the classes. So now footwear is having how many footwear values? Clogs and sandals. We have clogs and sandals. In clogs, we're having how many patterns? 1, 2, 3, and all the patterns T1, T5, T8. T1 student, T5 student, T8 student. All patterns belong to same class. That's why the node is labeled here. But if we talk about this pattern 1, 2, 3, 4, 5, these patterns do not belong to a single class. Now still we have to do. So now we can take this set as V0. So in V0, how many training patterns we have now? 1, 2, 3, 4, and 5. So in V0 earlier we had 8. Now in V0 we have 5. So how many attributes are left now? Habits and eats. So now we need to find the ratio of information gain of habits and eats for this set. So now if you find this one, these are the equation. Now if you find the ratio of information gain from here, keep in mind, from here, then the ratio of information gain for the eats is 0.673 and habit is 0.0208. So this is higher. So now it is so which attribute is taken? Eats is taken here. And it is having how many values? It's baked, roasted, and fried. So baked, fried, roasted. So we segregate. How many we segregate? 1, 2, 3, 4, 5 we had here. So 5 is segregated. So in baked T3 and T6 come. And they belong to same class, that is student. So labeled. Fried is having how many? T4 and T7. They belong to same class, professor. That's why their class it is labeled. Roasted only T2, and this one is already classified, right? So now all the nodes are classified. That's why this is the final decision tree. So if we have this final decision tree, now what we need to do? We need to make the rules. So how many rules we can make from here? One. This is if footwear equals to clogs, then student here. And for now, one rule for this one. So if footwear equals sandals, if it equals bed, then student, right? So another rule for this part. So if footwear equals to sandals and it's equals to fried, then it's professor. Then if footwear equals to sandals, it's equals to roasted, then it is professor. So how many rules we got here now? 1, 2, 3, and 4. So whenever some new pattern comes, we need to use these 4 rules, and then we can classify. And after training, we don't need to have the decision tree, all those computations. We have now simple rules only. So whenever R1 comes, just I'm talking about only one test pattern, R1 comes here. So which one we're having? Perspective with footwear. So footwear is what? Footwear equals to clogs. So footwear equals to clogs. If it is clogs, then classify this. That's why classification of R1 is student. One more. So R2 here. So footwear is what? Sandals. So footwear, yeah, sandals. After sandal, which one? It's equals to its. Then the next activity is its. So its we have here. So its here. We know which one we have roasted. Yeah, roasted here. So if sandal roasted, then class is professor. In that way, we classify R2 in class professors. In the same way, we classify R3 and R4. And finally, thank you. Thank you, thank you all. Thank you for your patience.
Yeah. Yes, thank you very much, sir. So we have got few questions in the chat box also, and most of the questions are actually related to this initial phase of, I mean, like which we have discussed, which are related to feature extraction. So let me take the latest question, and the last question which is posted in the last question asked, in what scenario feature selection performs better than feature extraction, and vice versa. So what are the two scenarios where for I mean where we can prefer feature selection, and other scenario where we can prefer feature extraction?
Yeah, good. It's a good question. So,
Yes.
if the problem is say image kind of thing, right? One is image kind of in say image processing, the feature extraction is required because we don't have any features. Again, I'm talking the whole discussion. I'm talking. So if we have the images doesn't have any feature. So now we need to extract the features from there. So in that scenario, which is required, number one. Again, feature extraction doesn't tell that from image processing only we're extracting the features. Feature extraction is talking we are having n number of features, but we are making some new m features where m less than n. The number of m is less than n. If number of features are very huge and very high, especially this image extraction is used in case of image processing where actually we don't know whichever information features we extracted, whether these features are right feature or wrong feature, whether this feature is exact or not, we actually don't know. Because whenever we do image processing, we extract some features from the faces or any kind of images. We extract those features. And now if in this scenario, if the number of feature becomes very huge, say it becomes a 20, 30 like that. So in that case, and we want to make say image compression kind of thing. You try to understand feature extraction is used in some places where we need to do some compression kind of things, image compression. We need to send here to somewhere else. Then we have to compress the image. So in that case, what actually we do? We use different kind of image extraction methodologies. For an example, PCA, LDA, principal component analysis, LDA, linear. This one I forgot. So a PCA, the principal component analysis. In that case, actually, what we do, we find eigenvalue and eigenvectors. Again, eigenvalue is talking about the prime value or the prime factors. So in that case, actually, if we have the 30 features, we want to reduce it because we need to compress it, because we need to send it somewhere else. Again, I'm telling one thing, whenever we have n number of features and we're going to create new m number of features where m less than n, then it is guaranteed that some kind of information we are going to lose if we do forcibly. But keep in mind, in some cases where we need to have the application of image compression, in that case generally we do. So keep in mind, if our objective is to compress the information or compression kind of thing, then we need to do image extraction.
Right.
And feature extraction. And feature selection is the thing. For an example, we are having the application of say text analysis, GIS system or DNA microarray data. Try to understand when we do say sentiment analysis kind of thing, or text categorization kind of thing. So we have different kind of keywords from the text. So now from one text, because our objective is to text categorization, so we can have the number of million of text. So now if all the text, if we keep all the keywords, then the whole matrix becomes very skewed. So in that cases, if the number of features is very huge, and due to some, because due to the increased number of features, somehow the accuracy is going to be biased. In that case, generally we do feature selection.
Right.
Whether am I clear or not, I don't know. That I am
Yes.
clear. Whether you are clear or not on that.
Yes. So I think with this we can conclude the session, because we are going out of, beyond the time, and naturally Dr. Saroj is with us for the tomorrow morning session also. So I have noted down those three remaining questions, and I will be discussing these three questions in the tomorrow's morning session, when we will have again Dr. Saroj with us. So I think with this we can. So thank you very much, Dr. Saroj. We will be connecting tomorrow morning session also with you. And thank you for today's this morning session. We have taken out a lot of fundamental details about the machine learning techniques, and particularly in the decision tree, and how it can be implemented, and how this concept of information gain can be used. So because from the last 1 year, I'm also exploring this field of data evaluation. So this decision tree and this information gain is quite helpful in that area. So I think with this remark, I want to thank Dr. Saroj. So thank you, sir, for this session.
Thank you,
Yeah,
sir.
so we will be connecting tomorrow morning session also with you, sir.
Okay, thank you, sir.
Yeah.
Thank you, everybody. Thank you, all the
Yeah.
participants.
So with this, I want to conclude the session, and let's close this session right now, and we will be connecting for the second session of the day. Thank you very much.